Good morning. Today we're going to talk about factoring still, but a very specific, very special case called the difference of squares. So we're still factoring, these terms, these polynomials that we've been doing, but in this special case, you'll notice something in common. So remember to pause the video at any time that you want to write things down before, listening to the lecture. Okay, so if you remember our standard form of these quadratic functions, right? That's what we're working with. Ax squared plus bx plus c, right? That's what we've been factoring. The b value in all of these very special cases is 0. There is no b value, and you'll see that in all the cases. So, and then the other thing to pay attention to is I have this list over here, 1, 4, 9, 16, 25. Those are my lists, I even wrote it here, of all my perfect squares. And that's what this means. It says the difference, so subtraction, of those perfect squares. And now why are they perfect? Like, what does a perfect square mean? Well, if I pick any number, let's say I pick 36. 36 is perfect because 6 times 6 is 36. And on the contrary, if I took the square root of 36, I would get 6. Right? If I pick 37, that's not a perfect square because you took the square root of 37, you get 6 point da 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 da, right? Something that goes on forever and ever. So these are very special because they are perfect squares. And that's what's going to happen here. You're going to notice this pattern. All right, so if I'm factoring, that means I need something in this binomial, right? A binomial times a binomial. And to start thinking, before we even get to x gains, how do I get x squared? Well, that's x times x. How do I get this negative? I have a plus and a minus. But what numbers will go there that will make this equation true? Well, my C value, if I'm playing X games, my C value is that negative 100 because there's no X value attached to it. My B value isn't there. But I already told you, all the B values in this are going to be 0. So what multiplies to negative 100 and adds to 0? Well, it's that perfect square for that reason, because 10 times 10 equals 100. And when you subtract, because one has to be positive and one has to be negative, when you subtract 10 and 10, you get that 0 pair. Okay, so those are our factors, but I gotta tell you, I'm not gonna use X games for this. This is the case where I don't have to use X games because I have a perfect square here. And let's talk about that. Why is x squared a perfect square? I can even add that to my list of perfect squares. X squared, even x to the fourth is a perfect square because it divides by 2. X to the sixth because it can divide by 2. So any multiple of 2 is also a perfect square, like x to that value. So I have a perfect square minus difference, a perfect square. And then let's look at what happened. The square root of x squared is x times x. 10 times negative 10 is that negative 100. And then if you wanted to test it out, right, and do your FOIL, x times x is x squared, x times negative 10 is negative 10x, 10 times x, 10x, 10 times negative 10 is that negative 100. If you use the box method, FOIL method, I don't care. But either way, if you notice, every time that middle will cancel and you're left with the first and the last term. So really, we just need them to be the same, but opposite. If you notice, it's x plus 10, x minus 10, same, but opposite, right? So let's see how that applies here. Looking at number 2, it says 4x squared minus 1. Do I have perfect squares? Oh yeah, 4 is a perfect square, x squared is a perfect square, and 1 is a perfect square. And most importantly, does it have a minus sign in the middle? Sure does, yep. So because of that, I can use my trick here.
Tap on it.
Can use my trick here, where I think of, okay, what times itself, has to be itself, gives me 4x squared. So I have 2x times 2x. It's got to be the same, but opposite. And then what times itself gives me 1? 1 times 1. So you could test this, you could do the box method to check, but basically if you notice, 2 times 2 is that 4, x times x is x squared, positive 1 times negative 1 is that negative 1.
Let's act it out and make patterns to solve this one.
Okay, so then number 3. This isn't so easy. They're bigger numbers, so really, like, that's why difference of squares is so important for cases like this. Could we have done X games for both of those and my feet don't stink? For sure. But when it gets this big, the numbers get challenging. So is 16 a perfect square? Is 49 a perfect square? Sure is. So because of that, I have to just think, what times itself, it has to be the same number, it won't work. What times itself gives me 16? Oh, 4 times 4. X is along for the ride, right? 4x times 4x is 16x squared. And then I have a positive times a negative. What times itself gives me 49? 7 and 7. Done. So this is fast, right? Difference of squares and understanding is very fast. Now let's go here. I have 3x squared minus 5. It looks like the difference. I have a minus, but my 3, is that a perfect square? Is my 5 a perfect square? Even if just one of them was, this doesn't work. It's not factorable. Not factorable. And that's what I'm writing. Not factorable is the answer. And then lastly, number 5 here, I have 4x squared plus 25. If you got to look right away. You got to catch this. There's a plus. There's no sum of squares. It's a plus sign. It's not a minus. It doesn't work. You're done. Not factorable. So I wanted to make sure you saw the cases that are factorable and why that is, and then the cases that are not, right? They have to both be perfect squares and addition. Now 4 and 25, that's a perfect square, but it's not subtraction. It said that backwards. It has to be subtraction, and it's not. It is addition. All right, awesome. Hope this helped.